Welcome to our YouTube channel. In this video, we are going to look stage 5 of a substation gantry structure loads using European standard EN 50341 part 1. In this stage 5, we are going to discuss about dead load without ice, dead load with ice, wire tensions without deviation for various temperature such as 0, -20 and T minimum, and wire tensions with deviations at a temperature 0, -20 and T minimum, whereas T minimum is -40 degree we are considering for our calculation purpose. So this will vary according to the project locations. So from now we are going to calculate one by one load cases up to this 19 load cases. Minimum temperature can be applied directly to the structure in any 3D model softwares. So that we are not going to calculate now. So first load case, the preliminary load is load 1A is a dead load with no ice load. In this we are going to calculate vertical load alone. Of course that a dead load, that is a self-weight, can be in only vertical direction, f of z. So in that weight of conductor we are deducting this entire span 100 meter in one side with the span of insulator, which we had calculated already here. In similar ways, in substation side we are having 25 meter. So the same 25 meter also deducted by the insulator, a tension insulator. So likewise the span is calculated as a 50%. So as it is going to handle some 50% of span in other support side. Maybe in one side it is a transmission line tower, another side it may be a different substation structure, and multiplying that into the self weight, that is the unit weight of conductor, where we are having the input here as 0.92 kg per meter, that is two numbers per phase of ACSR ostrich. So this mass kg per meter we already having in this table format, so that can be extracted from this drop down list. So likewise this a conductor load is calculated as 0.89 kilonewton. Similar like for weight of tension insulator, so the length, so here we need to just add this all the data. 97 is a hardware weight and 9 into 16 numbers, so that will give you the weight of a tension insulator. So we are considering the same tension insulator size for suspension insulator also. So tension insulator generally used to have two numbers, and suspension insulator is have one number per side. So totally it is 2, and the tension insulator is 2 per side, so it should be 4. And there is a weight of linemen with the tools at the mid phase to be considered. This is as per class 4.2.6.2 of European standard. So this is a class 4.2.62, you can see in the screen. So the characteristic erection and maintenance load on cross arms shall not be less than 1 kN. So we are considering 1 kilonewton here. By adding this conductor and insulator at end span, we are getting 13.27 kilonewton. This 1 kN we are going to add only in the mid span, so it is 14.27 kilonewton. Similar like for earth wire load also, we need to find out the vertical load considering the self weight, and here we need to consider the entire span 100 meter and 25 meter respectively, and with the weight 0.486 kg per meter, which we had find out here. For sustain it is 0.486 kilogram per meter. So this is we already having in this table. So multiplying with the mass per meter into this span, we are getting 0.3 kilonewton. So this is a summary for the same. So there is no horizontal forces Fx and Fy for both conductor and earth wire, that is on girder and tower, and only in vertical direction at mid space it is 14.27 and 13.27 for girder. For tower it is 0.3 kilonewton. Similar like next one we need to calculate for dead load with ice. In this case we are already having this weight. We are going to consider the span as earlier seen like in a dead load without ice. In that we had deducted that tension insulator span to the overall span of the conductor 100 meter and 25 meter in substation side. Only thing here change is the weight which we got considered is 2.01. This is nothing but in input data we have already calculated based upon the ice covered thickness which is calculated in wind, ice and loads. Here you can see that the diameter of the equivalent ice covered diameter is 68.01. With this, by multiplying this diameter as a in area formula called by d square by 4 and with the volume mass 300 kg per meter cube of ice density, and adding those value into this 0.98 kg per meter of conductor weight, we can get this 2.01. So this 2.01 again multiplied into this span, effective span of a conductor in both the side, we are getting 2.14. Similar like for a tension insulator, the value became same as we calculated in dead load with no ice condition, because the insulator is made up of porcelain or any glass polymer material that will have some sliding property or low in friction. So that will induce the total ice or snow to fall down, which never carry the weight much when compared to a conductor, because conductor span is going more than 10 meter or more than nearly 100 meter in one transmission line side, and another side it is 25 meter what we had considered for calculation. So again the linesman with the tool to be considered. So 14.43 kilonewton is at end span, and mid span it is adding this 1 kn 15.4 kn. Similar like for earth load also we need to consider the weight as ice cover weight. So for normal condition it is 0.486, and here we need to consider 1.56. That is what we got calculated here in input data, 1.56 kg per meter. So this is also in similar way what we got calculated for conductor, considering this equivalent ice cover thickness. So here you can see it's a 67.42 mm. So these are the summary for dead load with ice load conditions. So similarly here also there is no Fx and Fy, that is horizontal forces for both the tower and girder, but only in vertical direction F is at end phase 14.43 and in mid space it is 15.43. For tower top 0.96 kilonewton to be considered. Then next one we need to check. So in this 1A and 1B we had calculated. Next one is 2A, 2B and 2C. So let me see how to calculate those. For load 2A, it is nothing but it is a conductor wire tension. Both conductor and earth wire tension we need to calculate. That too with respect to their horizontal and vertical deviation. So here both horizontal and vertical deviation is 0 we are considering. So we know that at 0 degree Celsius, we are already having in our input data, at 0 degree Celsius it is 20 kilonewton. Similarly for earth wire it is 5 kilonewton. So here we can consider directly the longitudinal loads, that is perpendicular to girder span, we can consider as a 20 kilonewton directly, as we are having both horizontal and vertical deviation as a 0. There is no horizontal transverse loads. Similarly, there is no vertical load also, as the vertical angle is 0. For horizontal loads on earth wire, we need to consider that 5 kilonewton which is provided in the input. We can consider directly this longitudinal loads alone. So this is a summary for the same. For girder, we are having Fx alone is 20 kilonewton, other than Fy and Fz are 0. Horizontal force for tower is 5 kilonewton, that is due to earth wire, and there is no vertical force Fz and horizontal force Fy. So similar like for minus 20 degree, we need to consider by considering the value of minus 20 degree. So this should be minus 20 degree value, that is 30 kilonewton. So here also we can consider only the horizontal longitudinal force F of x, similar like last load case we seen. So only thing that value we need to consider is for minus 20 degree Celsius. So similar like for earth wire load also, we used to have only 10 kilonewton, that is for minus 20 degree Celsius here. So there is no F of Y and F of Z. So these are the summary for the same. So next is we need to find out the wire tension for minus 40 degree Celsius. So minus 40 degree Celsius we are having 50 for conductor and 20 for earth wire. So the same value we can consider as similar like 2B and 2A. Only F of X is applicable for this case, as there is no vertical and horizontal deviation. So here is a summary: 50 kilonewton and 20 kilonewton for girder and tower respectively. So now we had completed up to this 2C. The next one is 2, 3, 2B, 2C we are going to calculate. So this is nothing but it is going to be have a conductor deviation. So here same 2A, 2B only. Only thing the change is we are going to give here a horizontal and vertical deviations. As you can see in the right hand side picture, the 30 maximum 30 degree deviations means the conductor which is running perpendicular to girder has some deviations due to the location of other end structure. So that should not go beyond 30 degree. So here in this normal 0 degree 0 horizontal and 0 vertical, you can see here in plan view that conductor is directly perpendicular to a girder span. Similar like in section for vertical deviation, you can see that a conductor is running directly perpendicular to the axis of tower. So if these are the two cases, then we can directly have without deviation, we can say it as. But in 3A, 3B, 3C, we are going to see conductor deviation with 0 degree Celsius, 20 degree Celsius, that is minus 20 degree Celsius and 40 degree Celsius. So now we need to understand how this cos and sin h and cos and sin we need to apply here. In plan view, suppose there is a deviation, horizontal deviation on the conductor. Say for example, it should be considered as delta h. Then the axis to be considered for f of x force should be cos delta h. So f to be multiplied with the cos. In the other transverse side y direction, sin OH to be multiplied with f. So this is a parallelogram theorem. So similar like for elevation view, when there is a vertical deviation of conductor, cos V to be considered for both the horizontal axis x and y. And for vertical it should be sin phi V. So that phi or theta is a angle. So here we had mentioned. So the formula is arrived like that. For horizontal longitudinal loads, we need to consider the F, that is tension load for 0 degree as a electromechanic input we are having here. That should be multiplied with the cos theta V and cos theta H. Theta V is a vertical deviation. So by multiplying these three values, we are getting 15 kilonewton. Similar like for transverse side, it is cos theta V into sin theta H. Similar for vertical load, it is F into sin V. The same formula we are going to apply for earthware also. 5 kilonewton is for 0 degree Celsius, which is a electromechanical input for wire tension, and multiplying with the cos theta V and cos theta H, we are getting 3.75. The same multiplied with the cos theta V and sin theta H, we are getting 2.17. So phi into sin theta phi is a vertical force for tower. So these are the summary. So 15 fx, 8.67 fy and 10 fz. So these are for girder. Similar like for tower, f of x is 3.75 and f of y is 2.17 and finally f of z is 2.5. With a similar fashion, we need to consider for minus 20 degrees Celsius also. So again, it is for minus 20 degree, it is 30 kilonewton. That's electromechanical input we are having for conductor, and for earthwire it is 10 kilonewton. So multiplying with this cos theta value and sin theta value, we are getting these are the summary for conductor with 30 degree vertical and horizontal deviation having minus 20 degree Celsius. Similar like for 40 degree Celsius, we are having 50 kilonewton as a electromechanical input for conductor and 20 kilonewton for earth wire. By applying this in same formula cos V, cos theta V, cos theta H and sin theta H, cos theta V, and for vertical 50 into sin theta V, we are getting these values. And similar like for earth wire, 20 cos theta V, cos theta H and cos theta V sin theta H is 8.6. So this is a summary for the same conductor with the 30 degree horizontal and vertical deviation having minus 40 degrees Celsius. So under this minus 40 degrees Celsius of this deviations, these are the girder and the tower forces. So for f of x 37.5, f of y 21.66, and f of z vertical it is 25. Similar like 15, 80, 8.66 and 10 point, sorry 10. So these are the three division of load classes under load group 3. So we had seen up to 3C now. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.